Hello, how's it going? Okay, it's 2:30, so let's go and get started. All right, good afternoon, everyone. Thank you, everyone, for joining virtually for this lecture. How's everyone doing today?
Good, Professor. How about you?
Good to hear. Yeah, it's been a while since I've done work from home. It's weird, we did this for like a year and a half, and then now we're back. But I kind of miss a lot of things about working at home. I love seeing you guys, of course. I love coming to the classroom and seeing all of your bright and happy faces. But to be honest, I don't love you guys that much. I love my home a lot better than that. Okay. The plan for today is we're going to finish up our lecture notes on heat exchangers, and so we're about halfway done. And so we have a couple examples we're going to go through and a couple extra concepts. Okay. I forgot to do this on Monday, but homework 6 was posted just yesterday evening. And so that homework is going to cover free convection and heat exchangers. And so make sure you guys are working on that because that's going to be due next Wednesday. Okay. So you guys have about a week to do it. Okay. I think that's it for all my announcements. So are there any questions I can answer before we get started? Okay, all right, so let's go ahead and continue where we left off. All right, so the very last thing that we did on Monday was we were talking about the counterflow heat exchanger, right? And so what we said was that compared to our parallel flow, counterflow heat exchangers have the two flows going opposite directions, right? So you have one flow that's coming from left to right, the other flow that's going from right to left, okay? And you end up with a temperature profile that looks like the following, right? And so the thing that's unique about the counterflow heat exchanger is that you have a much more consistent temperature difference in between your flows, right? Because we know that when the flow comes in, so when the hot flow comes in on the left, right? It's at its hottest temperature as it could be, and then as it flows through the heat exchanger, its temperature is going to decrease, right? And so that's what we see here on the top curve here, right? The cold flow, on the other hand, is going to come in from the opposite side. It's going to start out really cold, and then it's going to warm up as it goes through the heat exchanger. And so you have almost these like two parallel curves that are running next to each other, and the difference in between them is almost constant. Not quite constant, but pretty close to constant. Okay. And so I think the question is that I think conceptually it makes a lot of sense what the difference is between these heat exchangers. But what does that actually mean in terms of practicality, right? And so when would you use one heat exchanger over the other? Okay, and so let's do kind of a direct comparison between the two, right? And let's take a look at what are some situations you would use one over the other. And so I think to facilitate this discussion, I think it would be good to kind of draw both of their temperature profiles so we can compare them kind of side by side. Okay. All right, so here are our temperature profiles, right? And so we have temperature on the y-axis and distance on the x-axis. On the left here, I'm going to draw the temperature profile for a parallel heat exchanger. And the right will be the temperature profile for the counterflow. Right? So the parallel heat exchanger, remember what's unique about that is that both the inlet of the hot and cold fluids are matched up together. Right? And so we have TH inlet, right? Starting out really hot. And then the cold inlet is going to start really low, right? And then as the two fluids kind of flow next to each other, they're going to exchange heat, right? So for the hot fluid, it's going to decrease in temperature. Okay. All the way up until the outlet temperature, THO. Okay. And then the cold fluid is going to heat up, and so it's going to increase in temperature, something like that. Okay. Up until its outlet, right? And let me draw arrows on this just so that you can see what temperature the fluid is going. And so remember, for parallel flow, both fluids are going in the same direction. Okay? And so here we assume that's going to be left to right. All right, so let's do the counterflow heat exchanger. And so we just saw this, but let me just go ahead and draw it again. And the cold fluid, we're going to start on the right side and then come up just like that. Okay. And we'll draw arrows just like the other side to indicate the direction of flow. Okay. All right, so what's the difference in between these two graphs, right? Let's start with the parallel flow. And so for parallel flow, you could see that the delta T here, or the difference in temperature that you experience, is massive at the beginning, okay? And remember, when you have a large delta T, that means your heat transfer is going to be very large as well. Okay. Okay, so what we can say is that we have a very large Q, a very large heat transfer rate at the inlet of our heat exchanger. Okay. But at the outlet of the heat exchanger, you know, the temperature difference is a lot smaller, right? And so what we can say is that for you know, for the later parts, you know, the delta T is going to be you know, not as effective. Okay. And so we have a small Q near the outlet of this heat exchanger. All right, and so if we rate, and so you know, if we say that the heat exchanger is most effective when it's transferring the most heat, what we can say for parallel flow heat exchangers is that they're most effective very much near the inlets. Okay. Okay. Let's look at the counterflow heat exchanger now. And so for the counterflow heat exchanger, we see that the delta T is a lot more consistent throughout the device. Okay. And so as opposed to the parallel flow where you start out very big and it goes down really small, the counterflow heat exchanger is going to be a lot more consistent all throughout. Okay. And so it doesn't really matter, you know, if you look at the inlet or you look at the outlet, you know, the performance there is going to be the same, okay? But what this does mean is that, you know, if you, because this delta T is a lot more consistent, naturally, if you make the counterflow heat exchanger longer, you know, let's say that you make it twice as long, then it's going to transfer twice as much heat, okay? And so the way that we could put that with words is that for a counterflow heat exchanger, it's the amount of heat that gets transferred scales very well with the length of the heat exchanger. Okay. Excuse me. And so for a counterflow heat exchanger, you know, there's that sense of, you know, if you make the counterflow heat exchanger twice as long, you're going to be twice as effective, right? You're going to transfer twice as much heat. You don't have that same notion for the parallel flow, because if you make the parallel flow heat exchanger twice as long, you know, you kind of get diminishing returns as you make the parallel heat exchanger longer, because the delta T is going to be smaller, the longer and longer that you make it. And so you still do get more overall heat transfer for the parallel flow. It's just that it's just not going to be as efficient as the counterflow. Okay. And so with these in mind, this kind of gives us some criteria, or gives us some situations where one is better than the other one. Okay. And so based on the fact that the parallel flow heat exchanger is a lot more effective near the inlet, parallel flow heat exchangers work great when you don't have a lot of space. Okay. Okay. And so if you're limited in space, let's say that you're designing an engine, right, and you only have a certain amount of space where you could fit your heat exchanger, the parallel flow is going to be a better choice for you, because for that small amount of space that you have, you're going to get a lot more heat transfer than if you ran it in counterflow. Okay. Whereas counterflow heat exchangers are best when you want value, right? And so if you want to kind of maximize the total amount of heat transfer that you can do, and space is not really an issue, then counterflow heat exchangers are going to be better for that. Okay. Okay. And so kind of the upshot to this, or kind of the quick summary, is that short lengths, parallel flow; long lengths, counterflow. Okay. Because remember, the goal is to transfer as much heat as possible, for this device. All right. Any questions on this before we do an example? Okay. All right. So let's go ahead and do an example, so you can see how all the numbers for these things add up. Okay. And so in this example, let's say that we have a counterflow heat exchanger, and it's going to be used to cool motor oil. Okay. Okay. And so let's say that our heat exchanger looks like this. Okay. And so we have a concentric tube. Okay. So just like, we don't really have any other options, because that's the only geometry that we know. And so we're going to have an inner fluid and an outer one. Right. And so for this problem, we're going to say that the oil is our hot fluid. And so we're going to float in the annulus. Okay. And we're going to say that oil is going to flow from left to right. Okay. And to cool the oil, we're going to run some water in the inner tube, right? So we're going to have a cooling water on the inside. And since we're in counterflow, then that's going to run from right to left. Okay, so the inner diameter here, we're going to say is going to be 25 millimeters. And the outer diameter, so the diameter of the annulus, we'll say this is 45 millimeters. All right. In addition to that, we also know the inlet temperatures of the two fluids. Okay. And so since this is counterflow, the inlet for the oil is going to be on the left, right? So we'll call this THI. THI. Okay. And so we have THI for the oil. THI for the oil is going to be 100 degrees C. Okay. And the inlet temperature for the water, so the water is the cold fluid here, so we'll call this TCH, or TCI, excuse me. TCI is going to be 30 degrees C, okay? All right. What we're interested in computing in this problem is we want to compute the length of the heat exchanger that's required. Okay. The length of heat exchanger that's required to cool down the oil down to 60 degrees C. And so in other words, what we're saying is that we want to design this heat exchanger so the outlet temperature of the hot fluid is going to be 60 degrees C. Okay, so let's go ahead and just write that in right now. Okay. Okay, so the outlet temperature of the hot fluid is going to be 60 degrees C. All right. And one assumption that we'll make is that the wall that separates the water and the oil, we're going to assume that has negligible thermal resistance. Okay. All right. And so this is a a multi-step problem, and so we're going to take this one step at a time. But I think it's a good problem that kind of shows you kind of a big overall look at everything that we've learned so far. Okay. All right. So any questions on this before we get started? Okay. All right. So before we kind of get into the details of solving this, because there are quite a few steps to this problem, let's go ahead and map out where we're going to go. Okay. And so ultimately here we're interested in the length. Okay. Okay. And so we want to solve for L of some kind. And so in some sense, this is very similar to problem 2 on homework 5. And so if you recall from that problem, we were looking for length as well, right? And the way that we did that was that we use our thermal circuit. Okay. Okay. And so our thermal circuit here looks something like this. Right. And so on the one hand, if we ignore the conduction resistance of the wall, we're going to have a convection resistance of the oil, right? Say 1 over H oil and 1 over H water. Okay. Both multiplied by A. Right? And so what we can say is that Q, right, the heat transfer between the two fluids, between the oil and the water, is going to be the difference in temperature divided by 1 over A times H oil plus 1 over A times H water. Okay. Where the area here is the surface area of the surface that's connecting the two, right? Here we have a convenient case because we are assuming that the wall that separates the oil and the water has basically no thickness, so we can say there's no resistance, right? And so the A here is just going to be pi times the inner diameter times L, okay? Because that's the surface where they interact, okay? And so what we could say is that Q is equal to Q is equal to pi DI-L times delta T divided by 1 over H oil plus 1 over H water. Okay. Since we have a heat exchanger situation here, this delta T is not going to be any delta T. Remember, the two temperatures are changing between the two fluids. And so what we're going to say is that this delta T is the log mean temperature difference. Okay, so we'll call that delta T LM. And then what we can do from here is we could solve this expression for L. Okay. And so if we solve this expression for L, we have L is equal to Q divided by pi DI delta T LM, okay, multiplied by 1 over H oil plus 1 over H water, close parenthesis. Okay. Okay. And so this is one way here that we can obtain the length of our heat exchanger, right? And we did this all from the thermal circuit. Okay. All right, so all that's well and good. The problem here is that we know basically nothing of this, right? So we haven't really been given any of this information. And so a lot of this problem is solving each of these different components, right? And so, there's a lot we need to solve for here. So let me go ahead and circle all of them, okay? And I'll color code it. And so first we're going to need to solve for the convection coefficients in the oil and the water, right? And both of these we're going to solve, we could solve for them together. And this is going to be solved through a Nusselt correlation. Okay. We've done that many times so far, and so that's basically going to be our, our convection problem-solving methodology. Okay. Let's see, what else do we not know? We also don't know the heat transfer rate. Okay. Right. This is probably the easiest one to find out because we can find this out based on the inlet and outlet temperatures of the hot fluid. Okay. Right, because if you know the inlet and outlet temperatures of a fluid, then you can compute its, you can compute its, you can compute its heat transfer rate. Okay. And the last thing that we need here is the delta T LM, right, or the log mean temperature difference. In order to compute this, we're going to need to know the outlet temperature of the water. Or in other words, the outlet temperature of the cold fluid. Okay. All right. And so that's how we're going to solve this. And so, we're going to take this expression and kind of solve for each of these things kind of one at a time. Okay. Our question. So what is change of TLM? Yeah, that's the log mean temperature difference. So that's what we went over last time, right? And so if you kind of scroll back up in your notes, whenever you have a heat exchanger like this, delta T LM is given by this expression right here. And it has to do with the fact that since our two temperatures are changing, throughout the fluid, it's hard to come up with one single number that expresses the temperature difference. So we instead, what we do is we compute this log mean temperature difference. Yeah, but in order to do that, we have to know what the outlet temperature of the cold fluid is going to be. Okay. All right, so let's go ahead and start solving these kind of one by one. So let's start with the convection coefficients because I think that's the most familiar thing that we have. Okay. Okay. And just like we have been doing for the last few weeks, we're going to compute this using our convection problem solving methodology. All right. So let's do step one. Okay. Step one is always going to be identify the situation. Right. We have two situations here, and so we have the flow of the oil and the flow of the water. Right. All right. So let's start with the flow of the oil. Right. And so we have an internal flow. And since the oil flows in the outer ring, what we say is that oil flows internally in an annulus. Okay. Remember last time that's we defined what that means, and then we know how to compute the neutral numbers from this. Okay. Right. And the water, which is inside the inner cylinder, this flows inside just a regular pipe, right? And so we've done this one before. Okay. So there is our situations. Okay. All right, next step is we're going to compute the fluid properties, right? So let's start with the oil. Right. Now to evaluate fluid properties, we have to compute its film temperature. And so luckily for the oil, we know what the inlet and outlet temperatures are. And so the oil is coming in at 100 degrees C and it's exiting the heat exchanger at 60 degrees. And so its film temperature, we can say, is kind of right in the middle. And so we're going to evaluate our oil properties at 80 degrees C. Okay. All right, and so if we do that, we end up with the following properties. And so you can look this up in a table. And for this particular problem, I use table A5 in the book. Okay. And so we have CP is 2131 joules per kilogram K. Okay. We have a dynamic viscosity of 3.25 times 10 to the minus 2 Newton second per meter square. Okay. And we have a thermal conductivity of 0.138 watts per meter K. Okay. All right, so now let's do the water. And so for the water, unfortunately, we don't know the outlet temperature of the water. And so we have to kind of make a guess here. And so we do know that the water comes in at 30 degrees C, right? So that's the inlet temperature of the water, right? And we know at some point the water temperature is going to raise, right? And so by the time the water reaches the outlet, its temperature is going to be higher than the inlet, okay? And so we have to make an assumption here. And so let's just go ahead and assume that the water temperature is going to raise by 10 degrees C, okay? And so with that, we can specify a film temperature here of 35 degrees C, right? But let's make a note here that this was assumed, okay? All right, so under these conditions, we have a CP. We have a CP of 4178 joules per kilogram K. Okay. We have a dynamic viscosity of 725 times 10 to the minus 6 Newton second per meter square. Okay. And we have a thermal conductivity of 0.625 watts per meter Kelvin. Okay. And so those are the properties that we're going to use to compute everything down the line. Okay. All right, so now let's do step 3. So step 3 is compute the Reynolds number. Okay. And so let's go ahead and compute that. So we know the Reynolds number. Let's do it for the water first, because that one's a bit easier, right? Because we've done flow in a cylinder before. Okay. So I'm kind of reversing the order a little bit here. So this is for the water. Okay. And so for the water, we know that the Reynolds number based on the diameter is equal to rho times the mean velocity times the diameter, inner diameter, divided by the viscosity. Okay. And oh, actually, I forgot to. I didn't give you the mass flow rates. Okay. So let me just go ahead and write it here. Okay. And so let's assume that the mass flow rate of the water, is 0.2 kilograms per second. Okay. And so based on that, the UM of the water, okay, the mean velocity of the water is going to be, we take our mass flow rate, m dot, and we divide it by the density of the water multiplied by the cross-sectional area, okay? Where the cross-sectional area for a pipe like this is pi over 4 di squared, okay? Okay, and so let's go ahead and plug it in here for UM. We know the density from the properties, or at least we should. I forgot to write it down, but we also know the density, right? That's one of the properties that we looked up from the table. And so if we plug that in and we plug in the diameter, what we get is a Reynolds number of 14,050. Okay. And since this number here is greater than 2,300, we know that the flow internally in this pipe is very turbulent. Okay. All right, so now let's do the oil. Okay. And so for the oil, when we compute the Reynolds number, we have rho times the mean velocity, okay, times the diameter, divided by mu, so same as up there, okay? But remember, you know, the oil is flowing inside an annulus, right? So it's not exactly a pipe. Okay. We know that annulus flow looks something like this, right? So we have flow in a donut, right? Okay. So this here is di, and the outer diameter here is do, okay? And so the question is, you know, when you compute the Reynolds number for an annulus, you know, what do you use for the diameter? The diameter that you end up using is something called the hydraulic diameter. Okay. Okay. I have no idea why it's called that. It doesn't really have anything to do with hydraulics, you know, but that's just kind of the name given to it. And so the hydraulic diameter, it sounds a lot cooler than it actually is. And so, you know, we can see here from this image that the flow is flowing in between the two diameters, right? So between DO and DI. And so we can define DH to be DO minus DI. Okay. Okay. And so that takes care of that. Right? And so that takes care of the hydraulic diameter. And so the other thing that we're going to need is the mean velocity, right? And so for the mean velocity, we're going to need, of course, the mass flow rate. Okay. And so the mass flow rate of the oil, we're going to assume it to be 0.1 kilograms per second. Okay. That was supposed to be given to you in the problem, but I just kind of forgot about it. Okay. And so just like up there, we're going to say that the mean velocity of the oil is going to be the mass flow rate of the oil divided by density times the cross-sectional area. Okay. Where the cross-sectional area, you have to be a bit careful for as well, because we're flowing in an annulus. And so the cross-sectional area is the difference between the outer area, which is pi over 4 dO squared, minus the inner area, which is pi over 4 di squared, right? Because we don't have any annulus flow inside the inner diameter. Okay. All right, and so if you plug all those in, you plug in for the hydraulic diameter, you plug in for the mean velocity, you get a Reynolds number of 56.0. Okay. And of course, this number here is much less than 2300. And so in our annulus, we have laminar flow. Okay. All right. Any questions on this? Okay. Okay, so that's step 3. So now that we know the Reynolds number, we are set to compute the Nusselt numbers. Okay. Okay. And so again, we'll do this kind of one at a time. So let's do the water first. And so for the water, we know for its turbulent flow, okay. And so for turbulent internal flow, our Nusselt correlation here is NUD is equal to 0.023 times the Reynolds number based on the diameter to the 4/5 power multiplied by Prandtl number to 0.4. Okay. Right. In this particular case, the water is being heated up, right? And so the water is starting out cool, and then it's heating up as it flows to the outlet, right? And so that's why we use a coefficient or an exponent of 0.4 here. Okay. And so we plug in for all the values here, we get a Nusselt number of 90. Okay. And then for the oil, we know that we have laminar flow in an annulus. Okay. And for these situations, if you remember from Monday, the way that we compute these Nusselt numbers is we take the ratio between the inner and outer diameter. Okay. And so we plug that in for this problem, we get 0.56. Okay. We then take this number and we look it up in the table. Okay, and we went over this table on Monday. And so if we do that, we get a Nusselt number. The Nusselt number is going to be 5.74. Okay. Okay. And so now that we've done that, we can go ahead and compute our convection coefficients. Okay. And so let's start with the water. Okay. And so the convection coefficient for the water is going to be Kf divided by di times the Nusselt number. Okay. And since our Nusselt number is 90, right, we go ahead and plug that in along with our inner diameter. We get 0.2250 watts per meter squared Kelvin. Okay. Now we do the same thing for the oil. And so we have H oil is equal to K divided by DH. Remember, DH is our hydraulic diameter. Okay. And we multiply by its Nusselt number, which is 5.74, and we get 39.6 watts per meter square Kelvin. Okay. All right, so that's two pieces of the puzzle, right? And so now that we have both convection coefficients, we can compute the total. You can think of it as the total thermal resistance for this problem here. Okay. All right, any questions on this so far? So the question is H water technically still a gas? Yes, that is, it is true. And so, we still don't know the outlet temperature of the water just yet. And so this is still a guess. And so if you wanted to be really careful with this problem, typically these are solved iteratively. So anytime you have to kind of make a guess like this, you kind of make a guess, you solve the problem, you go back and you check and see how good your guess was. And if it was off, then you go and you kind of redo the problem from there. And so yeah, so this H water is still pretty tentative, until we find out what the outlet temperature of the water is. Yeah. Yeah. Okay. All right. So that's the convection coefficients. And so the next thing we're going to compute is we're going to compute the heat, the total amount of heat transfer in this heat exchanger. Okay. Okay. And so, just to kind of remind ourselves, let me just scroll up for a bit, right? The formula that we're working with is this one right here, right? Because ultimately we're solving for the length. And so, we've computed H water, H oil, so those two are good. We can go ahead and check them off. And next we need Q and delta TLM. And those two are related, right? And the first thing we can compute is the Q, okay? And the way that we're going to compute this Q is we're going to compute it based on the, based on the temperature change in the oil, okay? Because what we know is that Q is equal to m dot Cp times THO minus THI. Or I guess you could swap them in order to get a positive number. But we have everything here because we know THO here is 60 degrees C, and we know THI is 100 degrees C. Okay. We know the mass flow rate. So the mass flow rate of the oil is 0.1 kilograms per second. And we know Cp. Cp was a property that we looked up earlier. Okay. Right. So we have everything that we need here. And so if we go ahead and plug in all these numbers, we get 8,524 watts. Okay. Technically, I know you get negative because you do 60 minus 100, but we'll just make it positive. I kind of mixed up the signs for that one. Okay. Right. And so that's the Q that can go into our length equation, but we can also use this Q to compute the outlet temperature of the water. Okay. Okay. because we're assuming that this heat exchanger is perfectly insulated, right? And so that means any heat that gets lost by the oil is going to be gained by the water, right? So this exact Q, we could set it equal to, Q is equal to m dot of the water, Cp of the water, multiplied by TCO minus TCI. Okay. Okay. We know Q because we just solved for it, and so this Q is going to be plugged in here. Okay. And the only unknown in our equation is going to be TCO, right? And so if we solve for TCO, we get 40.2 degrees C. Okay. And so, Nick, coming back to your question from earlier, we end up seeing that our outlet temperature for the water is 40 degrees C. And so the film temperature that we use, which was 35, ended up being close to exact. Yeah. Yeah. This is an example from the book. And so, of course it works out perfectly because it's the book, right? But if you're doing a problem by hand, and if you're doing this for the first time, you might have to iterate, once or twice in order to get the appropriate temperature. Yeah. Okay. And so now that we have the inlet and outlet temperatures of both the oil and the water, we can finally use that to compute delta T Lm, right? Because delta T Lm, right? This is delta T2 minus delta T1, all divided by ln delta T2 divided by delta T1. Okay. Where delta T1 and 2 are going to be the temperatures, the difference in temperatures from the two sides, right? And so delta T1 is going to be temperature of the oil at the inlet minus temperature of the water at the outlet, okay? Because that's the delta T1, remember, is the temperature difference on the left side of the heat exchanger, okay? So remember, this is side 1 and this is side 2, right? And so side 1 being the left side, we take the temperature difference between, THI and TCO, okay? Okay. And delta T2 is going to be the temperature difference on the right side of the heat exchanger. And so this is going to be T oil out minus T water in. Okay. And so if we plug in for these, we get delta T1. Delta T1 here is going to be 59.8 degrees C. And delta T2 is going to be 30 degrees C. Okay. I might have swapped these on accident. Let's see. Oh no, they're right. Okay. And so we go ahead and plug that in. And we get delta TLM is 43.2 degrees C. So that's the log mean temperature difference between the two fluids. And so on average, between the two fluids, we have a temperature difference about 43.2. Okay. All right. And so now all the pieces have been assembled. So we finally have Exodia. Okay. And so we can go ahead and take all these pieces and plug them into our equation that we had at the beginning to solve for L. Okay. Okay. And so we plug it back in. Let me just scroll up so you can see the formula again, right? So we have L is equal to Q divided by pi di delta T Lm multiplied by 1 over H oil plus 1 over H water. Okay. We have all of those, and so we spent the last half an hour computing all of these. Okay. And so what we get from this is a length of 65.9 meters. Okay. All right, so it was a very lengthy example, but but we kind of saw a bit of everything here. And so, we got some more practice doing our convection problem solving. We did some practice with the new stuff with the heat exchanger. So this is a really good example. I know it took us a long time, but I think these examples are always good because it kind of takes you through the entire, basically everything, right? And so, if you kind of go through this example again, when you're doing your studying, this is a good one. I really like this example. Okay. All right, any questions on this example here? Okay. All right, so let's go ahead and move on to the next topic then. And so the next topic is called effectiveness of heat exchangers. Okay. All right. And so remember when we first started talking about heat exchangers, I kind of made the comparison that this unit is very similar to fins, right? Just remember when we went over fins, fins are kind of this very specific engineering device or engineering thermal, piece of engineering that you're going to use fairly commonly, okay? And so just like we looked at fins, right? We looked at them from a performance standpoint. We can look at heat exchangers from a performance standpoint as well, okay? Right, and so grammatical blip right there. And so in other words, when we design a heat exchanger or when we're assessing a heat exchanger, right, we want to find out how good is it basically, right? Because not all heat exchangers are the same. And so based on how it's designed and based on how what fluids are running through it, some heat exchangers are going to be better than the other ones. Okay. And so the metric that we use to assess its how good it is called effectiveness. Okay. Okay. And so effectiveness, we give the symbol epsilon. Okay. And epsilon here is going to be a number, right? So it's going to be a coefficient that's between 0 and 1. Okay. And what that coefficient represents is the following ratio. Right? And so in the denominator of this effectiveness, what we have is the maximum possible heat transfer that's theoretically possible with this heat exchanger. Okay. Okay. And so for every heat exchanger, we have what we consider to be the maximum theoretical Q possible. Okay. And in the numerator, what we have is the actual Q. Okay. All right. And so if you have an effectiveness of 1, that means your heat exchanger is the perfect heat exchanger. And so it's literally as good as it can be. But if you have an effectiveness of 0.1, then your heat exchanger is only 10% reaching that maximum. Okay. For heat exchangers, the maximum possible is actually very difficult to reach. And so let's define what that actually means. Okay. Okay. And so theoretically, the maximum possible heat transfer that you can achieve in a heat exchanger occurs in a counterflow heat exchanger with infinite length. And so under these situations, we can basically assume that the two fluids achieve thermal equilibrium, okay? Right, and so the two temperatures of the fluids end up matching because, there's just infinite length to do so, okay? Okay. And so the way that we can compute this, right? And so the way we can say is that the maximum Q is equal to, we're going to take the maximum possible temperature difference between them. And so the maximum possible temperature difference would be the difference between the two inlet temperatures, right? So we have TH in minus TC in, okay? Because basically, the two fluids are going to traverse that entire temperature spectrum. Okay. And then we're going to multiply this by m dot Cp min. Okay. Right. Okay. And so that's a theoretical maximum, right? And so there's, in theory, this is not achievable in practice, right? And so you can't have a heat exchanger that's infinitely long. Okay. Okay. And of course, you're going to compare that to the actual Q that you compute from the component fluids. Okay. And so you can do that either from the hot or the cold, right? And so it depends on kind of what you're given in the problem. And so, for example, for the last problem, we could compute the Q of the hot fluid, right? And so the Q of the hot fluid would be m dot Cp of the hot fluid, okay, multiplied by Thi minus Tho, okay? Or you can compute it from the cold fluid if you're given both of those temperatures, right? And so this would be m dot Cp of the cold fluid multiplied by Tco minus Tci, okay? So you can use either one of these, for the actual heat transfer. It really depends on what you're given in the problem. Okay. And so if you can compute one of these actual Qs and then you divide it by Q max, that's going to give you the effectiveness of your heat exchanger. Okay. Most effectivenesses, just kind of based on practicality, they're going to be in the, if you have a heat exchanger that's like 0.25, like 25% effectiveness, that's pretty good, all things considered. And so you'll see a lot of, and we'll do one more example here. I think the effectiveness that we have is about 6%, so 0.062. So that's not uncommon. So that's pretty normal. Okay. All right. Any questions on effectiveness here? Okay. Okay. But what if you want to compute effectiveness, but you don't have the outlet temperatures, right? So this is a very common situation. Okay. A lot of times, when you're designing a heat exchanger, you're going to know what your inlet temperatures are, and so you're going to know what temperature of what the temperature of the fluid is as it comes into your heat exchanger. But as to what comes out, sometimes you're not sure. Okay. Okay. And so the question is, can you compute this, without the outlet temperature? And it turns out yes. And so what people have done is that they've run experiments on lots of different designs of heat exchangers, and then they were able to come up with expressions for the effectiveness just based on that design. Okay. Okay. And so remember, a week ago, we talked about all the different kinds of heat exchangers that are out there. And so we talked about, concentric tube, which is the one that we're doing, but, we also talked about shell and tube. We talked about cross-flow heat exchangers, right? And so each of those have their own expression for the effectiveness. We're only going to go over the ones for parallel and counterflow, but there's a lot more out there. Okay? And so let's do parallel flow. Parallel flow concentric tube X. Okay. And so for a parallel flow concentric tube, our effectiveness is given by the following formula. Okay. And so you have 1 minus exponential of a new variable called NTU minus NTU. I'll define that in a second. Okay. Okay. We multiply that by 1 plus CR, and CR I'll define in a second as well. And we divide that by 1 plus CR. Okay. All right, so that's the effectiveness if you have a parallel flow concentric tube heat exchanger. Okay. If you have a counterflow concentric tube heat exchanger, your effectiveness is given by the following. So you have effectiveness is equal to 1 minus exponential of minus NTU times 1 minus CR, all divided by 1 minus CR exponential minus NTU times 1 minus CR. Okay. Okay. And so NTU is defined as the following. Okay. And so NTU stands for number of transfer units. And so it's kind of a way to express, the amount of heat or energy that gets transferred. Okay. All right. So NTU is defined as 1 divided by m dot Cp min. Okay. And so again, we see the minimum m dot Cp. Okay. And we multiply that by the total thermal resistance. Okay. And CR here is a ratio of the m dot Cp's. Okay. And so we have m dot Cp min divided by m dot Cp max. Okay. Okay. And so there's a lot of variables here. And so I do want to do one more example to kind of pull this all together. I don't know if we're going to have a chance to finish it, but we'll at least get a good head start on it. And so, we should be able to get as good enough head start where you can do the homework, but we'll finish up all the details of it next Monday. Okay. All right. Any questions on this before we jump into an example? Okay. All right. So let's start this example and then we'll finish it up on Monday. Okay. Okay, so for this example, we're going to have a parallel flow heat exchanger. Okay. Okay. And so our material here is going to be made of copper, right? So that's going to be the pipe material. Okay. And for this example, we're going to run water on both sides of the pipe. All right, and so we have our heat exchanger here, okay? And so for this particular problem, our inner pipe here is actually going to have a thickness. And so we're going to have to account for its conduction resistance, in the problem. Okay. And so we're going to have water on both sides. And so we're going to have, let's see, the hot water is going to be on the inside. Okay. And so the hot water is going to come in with a temperature of 50 degrees C. Okay. So that's going to be your THI. And it's going to be flowing with a volumetric flow rate. So big Q is going to be 15 liters per minute. And then we're going to also have water on the outer pipe, also flowing from left to right. Okay. The outer pipe flow is going to be 20 liters per minute. And the inlet temperature, TCI, is going to be 20 degrees C. Okay. All right, so let's put some dimensions on this. And so the outer diameter here, the very outermost diameter, DO, this is going to be 5 centimeters. Okay. The innermost flow right here is going to be DI. And so that's going to be 2 centimeters. Okay. And then we're going to assume the thickness of this wall, right? And so we'll call this little t. This thickness of the wall we're going to assume is 1 millimeter. Okay. And because we're going to need it later to compute resistance, the thermal conductivity of the copper pipe is going to be 400 watts per meter Kelvin. Okay, so that's all we're going to be given in this problem. And so what we want to compute, we're going to compute three things. Okay. And so first of all, we're going to compute the effectiveness. Okay. And then next, we're going to compute the total heat transfer rate, or the actual heat transfer rate. Okay. And then once we have that, we're going to use that to compute the outlet temperatures of the two fluids. Okay. Okay. All right, and so there's our setup. And so we're going to use our formula for the effectiveness since we know this is a parallel flow heat exchanger, and so we can use that formula there, and then we'll proceed from there to compute everything else. Okay. All right. Any questions on the problem setup? Okay. All right. So let's start with the effectiveness, and that's going to be the bulk of the work for this problem. Okay. Okay. And so for a parallel flow heat exchanger, the effectiveness is the following. So we have 1 minus exponential of minus NTU times 1 plus CR, okay, all divided by 1 plus CR. Okay. And so the goal here is to compute NTU and CR. Okay. And part of NTU, if we can scroll up a bit here, in order to compute NTU, we have to compute the total thermal resistance. Okay. So let's go ahead and work on that. Okay. And just like we saw in the last example, in order to compute total resistance, we're going to need the convection coefficients of the two flows. Okay. Okay. All right. And so let's go ahead and run through our convection problem solving methodology. Okay. Okay. All right, so first step is we're going to ID the situation. And so we have two flows here. And so we have flow in an annulus and flow in a tube. Okay. Okay. All right. And both our fluids here are going to be water. And so we're going to evaluate the fluid properties. Okay. Here we have a unique situation because both of our fluids are water. Okay. But they're at different temperatures. And so, if you wanted to be more, I should say, strict on this problem, you would compute two sets of water properties. So you do one for the hot water and one for the cool water. Okay. For this particular problem, I was a little bit lazy, and so we're going to compute the water properties just at one temperature. Okay. Right. And so what we're saying is that the hot fluid is coming in at 50 degrees C. The cold water is coming in at 20 degrees C. And so if we take the average between these, we get 35 degrees C. Okay. And so if we evaluate the properties of water at 35 degrees C, we get the following expressions. Okay. So we get Cp is equal to 4,200 joules per kilogram K. Okay. Rho is just about 1,000 kilograms per meter cubed. Kinematic viscosity is 1 times 10 to the minus 6 meters squared per second. Thermal conductivity of water is 0.6 watts per meter Kelvin. And we have a Prandtl number of 6. Okay. Okay. All right, so those are all the fluid properties. And so next thing that we're going to need to do is we need to compute the Reynolds numbers. Okay. And so for the Reynolds number, so we'll start with the inner pipe. And so the Reynolds number for the inner pipe is going to be the mean velocity times the inner diameter divided by the viscosity. Okay. Where the mean velocity here is going to be our volumetric flow rate that was given to us in the problem. And so for the inner flow, what was that? 15 degrees or 15 liters per minute. Okay. And then we just have to divide by the area. Okay. So the area for the inner pipe is pi over 4 EI squared. Okay. And so we plug in for that, we get a Reynolds number of 15915.5. Okay. And so we can see this is turbulent. Okay. I know it's 345, but let's go ahead and write out the Reynolds number for the outer fluid as well. Okay. Just to kind of put a pretty bow on this for now. Okay. Okay, so for the outer fluid, we have same thing. So we have UM times the hydraulic diameter divided by nu. Okay. So remember, this is flow in the annulus. Okay. And so UM here is going to be our volumetric flow rate divided by the area. Okay. And just like in the previous problem, we're going to do dO squared minus DI squared for the area. Okay. And so if we compute the Reynolds number for the outer flow, we get 5,835.68. Okay. And we see this is also turbulent. Okay. All right. So let's stop here. And so on Monday we'll finish this up. There's not that much more left. Okay. Because once you have the two convection coefficients, the rest are kind of just like, bang, 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 right? And so, just like all these problems here, the most time-consuming thing is just computing the, computing the convection coefficients. Okay. All right. Any final questions on this before we wrap it up for the week? Okay. All right. So thank you guys for tuning in, and thank you guys for being virtual today. I appreciate your guys' flexibility. And so Monday we'll be back in person, and so I'll be back in the classroom on Monday. But I'll have the usual Zoom thing as just as usual. So I hope you guys have a great day. Hope you guys have a good weekend, and I will see you on Monday. Keith, did you have any final questions?
No, sorry, I was just getting some notes down.
Okay, yeah, no problem, no problem. Take your time.
I got it. Thank you, Professor.
Yeah, no problem. Have a good weekend.
You too.